We are going to continue today about eigenvalue sensitivity from section 7.3. And so I simply added some slides to the file that we had last time, so there are no new bonus problem or I guess I changed the reading assignment. Also, I wanted to remind you that a week from today, we are going to have the second interim exam. I changed the order. Instead of having the review on Friday, I'm going to have the review on Wednesday. And this is because for the off-campus people, I'm supposed to have some additional time for them to absorb it. So when I teach a class off-campus, I usually try to have more of a break between the review and the exam. So that's about it. Any questions before we continue with eigenvalue derivatives? Oh, I already assigned another homework, which is due a week from today. It's just one problem, which is a modification of a problem in the textbook. And it's intended to also help you prepare for the exam. So sort of beside the bonus problem on eigenvalue sensitivities, there is an actual homework problem to do on that. So the last question that I raised is why bother getting sensitivity of eigenvector derivatives, and we discussed that last time, but I wanted to make sure that we revisit the question of what's the objective of getting sensitivities. So could anybody remind us why we are spending so much time on calculating sensitivities?
To see the impact of the change in the design variables.
Okay, but where are we going to use it?
Search directions.
I'm sorry?
Search directions.
Okay, so we are going to use it for search direction. Can anybody think of another application? Anybody experimental here?
Just cost and how much it will cost to change that.
Yeah, but no, I'm talking about an application that people do experiments often.
Parameter study?
I'm sorry?
Parameter study?
That's a bit too vague. I'm sorry?
Uncertainties.
Yeah, but could anybody be a bit more specific? Well, when you do experimental work and you measure something, you want to know what is the effect of errors on your measurements. And so one of the standard techniques is to calculate the standard deviation in the quantity that you measure in terms of the standard deviation of the quantities that are your input. So if you look for that formula, you'll find out that you need the derivative of the response with respect to your error. So for example, if you are calculating the vibration frequency from a frequency response function when there is a peak, then you may have some uncertainties about how you apply the excitation and how you measure the frequency response and how you read the graph of the frequency response to figure out where the frequency is, and so on. And now, in all of those, there is a basic assumption that you can use derivatives in an additive form. Does anybody know what I mean by that the gradient vector or derivatives can be added, or they are additive?
Linear?
I'm sorry?
Linear?
Linear in what sense?
Superposition?
Yeah, that is the basic assumption, and I want you to keep that in mind because for eigenvalues it breaks down, is that if we know the derivative in the x direction and we know the derivative in the y direction, we can calculate the derivative in any direction in the plane by simply doing a dot product of the gradient vector times the direction vector. So keep that in mind, and let's move. So the last thing that we did is look at this formula, which gives us the derivative of the eigenvalue, or the square of the vibration frequency, in terms of the derivative of the stiffness and mass matrix. And we concluded that just by looking at this formula, we can expect that, for example, if we have a cantilever beam, we will want to, if we want to increase the frequency, we'll change the stiffness where the elastic energy is maximum, and we'll change the mass where the kinetic energy is maximum. So for a cantilever beam, that would mean increasing the stiffness near the root and adding mass or subtracting mass near the tip. Now, let's move now to calculating derivatives of eigenvectors. We had two equations. One was the derivative of the equation of equilibrium, and one was the derivative of the normalizing condition about how big the eigenvector is. And if we collect them together, we get a system of n+1 equation for n+1 unknowns, where n of those are du dx, that is the derivative of the eigenvector with respect to the design variable, and the last one is the derivative of the eigenvalue, eigenvector and eigenvalue. And you can say, okay, this is n+1 equation with n+1 unknown. And the reason that it's difficult to solve it is because this principal minor, that is the n by n principal minor, is singular. And could anybody remind us why is it singular? Okay, let's go back a bit. When we solve this eigenvalue problem, how do we actually do that if we don't use if you had to do a problem by hand, let's say I gave you a 2x2k and a 2x2m, and you had to solve for the eigenvalue, does anybody remember how to do that? And? What do you mean solve for it? You calculate the determinant, and solve means an equation. What would be the equation? Yeah, but how is the characteristic equation related to the determinant? The determinant is, I'm sorry?
The determinant is the characteristic equation.
No, the determinant is a quantity. An equation has a left side and a right side. Equal to 0, okay? So that's what I was fishing for. We find mu from the condition that the determinant of this equation is equal to 0, which means that the mu that we find would make the determinant equal to 0. Which would mean that this part of the matrix has a 0 determinant, or it's singular. Okay, so it's like solving a system of equation where at the 1, 1 position you have 0, you want to start Gaussian elimination, and you'll need to start shuffling things. And we don't like to pivot or shuffle when we work with this type of equation because they are very sparse, and if you start pivoting them, you destroy the sparseness. So instead, The textbook, I don't want to go into the gory detail, but the textbook says, let's first solve the derivative not with the original normalization condition, but with a simpler normalization condition that says that the largest component of the eigenvector is equal to 1. If the largest component is equal to 1, what is the derivative of that component with respect to the design variable? 0, right? That is, we keep it at 1. And so that means that we can eliminate one unknown. Instead of using this equation and solving n plus 1 equation for n plus 1 unknown, we use only the top part. But in that top part, we can eliminate one variable and we can eliminate one row, thereby making this singular system not singular. And then we can solve it. And then once we solve it, we need to rescale the eigenvector to satisfy the normalization condition. And this is a bit of algebra, but this is Nelson's method. It was invented around 1976, if I remember right, and it's the mainstay of a lot of software that calculates eigenvector derivatives for sparse finite element type equations. So let's look at example 7.31. What we have here is two masses and three springs. Forget about the dash point. The dash point is there because in a later part of this section, we look at derivatives of damped frequency. So for this problem, C is equal to 0. Two of the springs have stiffness of 1, and we ask ourselves, what's going to happen when we increase or when we change this spring from 1 to k? So we are essentially looking for the derivative with respect to k. And could anybody tell me what we expect that is before solving the problem? What do we know about the derivative of the frequencies with respect to k?
Increases with increasing k.
Okay, we expect that the system becomes stiffer and we will get higher frequencies. Let's see if that is borne out. Anyhow, this problem was set up so that k is very simple. We have 2 degrees of freedom, which is the horizontal motion of mass 1 and the horizontal motion of mass 2. And then the stiffness matrix is this, and the mass matrix 1, which means that I've selected the two masses to have unit values. And then for k equal to 1, you solve it and you find that omega 1 is equal to 1, omega 2 is equal to the square root of 3. And this is the first eigenvector that correspond to the normalization condition U transpose mu equal to 1. What is the physical meaning of this eigenvector? Yes, but what is this mode shape? That is, how is the system vibrating in its lowest frequency? Yeah, so. And you can expect that the second vibration mode would have them move apart. And so if we use this normalization condition, we get this vector. If on the other hand, we use a normalization condition that the largest component is equal to 1, we'll just get the vector 1, 1. So these are two possible solutions of this problem. And if now we will calculate the derivative of the stiffness matrix, you know, it's just 1, 0, 0, 0, and M prime is 0, 0. And so mu prime is simply U transpose K prime U. And we will have the square root of 2 appears twice, and we'll get 0.5. And U bar prime is minus 0.5 and 0, and from which we'll get the U prime as square root of 2 minus 1 and plus 1. So as expected, we get that increasing K will increase the vibration frequency. What does U bar prime tells us about what will happen as we change K? What will happen to the vibration mode? Remember, the original vibration mode was 1, 1. And we have this derivative. What does it tell us, and why does it make sense?
Is the second mass unaffected?
No. Sorry, I did use ambiguity. Let's look at this one. This one is trickier because as we are changing the vibration mode, we keep the amplitude the same. What does this tell you that is expected? Right, that is what basically happens. Think about what will happen when K goes to infinity. If K goes to infinity, the leftmost mass will remain stationary. It couldn't move. So if K goes to infinity, what will happen is that only the second mass will vibrate. And so the derivative of U is basically, as you increase K, 1 moves less and 2 moves more in order to preserve the normalization. And so this is what you see in both of them. If you keep the amplitude the same, it just tells you that 1 moves less. If, on the other hand, you keep the kinetic energy the same, then 1 moves less and 2 moves more. Okay, so it's important, even if you were not able to observe the Coiter paradigm of knowing the answers ahead of time, you at least have to retreat to your second line of defense. When you look at the results that come out of calculations, be sure that you can explain them physically. Otherwise, okay, well, maybe you can feel it the otherwise. Why is it important that when you get results from calculations that you are able to explain them physically? Anybody see any self-interest in doing that? Okay, I mean, you improve your insight, which is sort of a motherhood kind of sentiment. I'm looking for something much more concrete. Yeah, that is the main reason for understanding things physically is because there is whenever you get results out of calculations, there is a good chance that they are the result of your error. And so if you cannot understand them physically, it means go back and look. Not only this, even if you have complete confidence in what you are doing, your boss your boss's instincts of self-preservation require him to ask you why you are getting those results, because he may not have complete confidence in your ability to generate flawless results. So you should expect to be able to explain why the numbers show up the way they are, and otherwise you can end up with a lot of egg on your face. Okay. Now, the thing that I like to do, as you probably have seen, is explore the fine print on the methods that we study. And with eigenvalues and eigenvectors, there is a lot of fine print that a lot of people ignore and end up with a lot of egg on their face. So the first thing that is the key to the problem is eigenvectors are not always unique. And the question is, when can we expect two different vibration modes with the same frequency? You may remember that my favorite example is my car. Can you think of a case where you would expect two vibration modes with the same frequency on a car?
Similar to, like, we take a sine wave like this, one could be like this.
Okay. So Satish basically described something where either the left side of the car vibrates or the right car of the car vibrates. If cars were completely symmetric, which they are not, you would expect that that could happen, even if they are not completely symmetric, if the vibration is very localized. That is, imagine that the vibration is localized to the glass of the rear of one of the rear doors. That is, somebody who designed that panel and made it vulnerable so that at 55 miles per hour or whatever, that glass begins to rattle because it's so localized and because there is not really any difference between the glass panel on the right back door to the one on the left back door. Maybe you will have those two eigenvalues, each one of those glass panes rattling at the same frequency. So symmetry is an important reason for having this problem. What else? Can you think of a case where it's not symmetry but something else that causes well, actually, the answer is here. So it is optimization which is causing it, but could anybody tell me why? I expect that the process that the engineers in Detroit use to protect you against your cars rattling at speeds that you normally drive at also create problems of different vibration modes having the same frequency.
Your tires. They balance the tires.
Now, this is again problems of symmetry, but I'm talking about problem of optimization. That is, imagine that somebody discovered that there is a problem at 55 miles per hour, though something in the car rattles. Let's say that it's your bumper. And they start doing things to the car, and the problem goes away, but I'm saying that in the process, it increases the chance that there will be two vibration modes with the same frequency. The question is why?
Is it usually symphony?
I'm sorry?
Do they usually have symphony to get rid of the problem?
Right. I mean, that's correct, but why would it create...
So that vibration's another part?
Yeah, that is what happens when you have vibration modes. You start analyzing, let's say, your car, and you find out that of all the vibration frequencies, one is a problem, it's too low, so you start pushing it up. Oftentimes what you do is, since you don't want to increase the weight of the car, you move some material from places that don't vibrate to places that do. In the process, you raise the frequency which is a problem and lower the frequencies that are not a problem. And so you may have started with two vibration frequencies that were 20% apart. By the time you are finished fixing the car, they are only 5% apart. And if you do the optimization really thoroughly, you can end up with them being equal. Now, equal vibration frequencies that you are likely to encounter all the time do something really nasty to programs like Abacus or ANSYS or Nastran that calculate vibration mode. And this has to do with the following. Vibration modes are orthogonal when the eigenvalues are distinct, but any combination of modes corresponding to the same frequency is also a vibration mode. And this equation is intended to show you that. I'm writing the equation of vibration mode 1 with an eigenvalue mu, and then I'm writing the equation of vibration mode 2 with an eigenvalue mu. Then I take alpha times this equation plus beta times the second equation and add them together. And I found out that alpha u1 plus beta u2 is also a vibration mode. Now, this means that when the two vibration frequencies are the same, and you ask a program like Abacus to calculate for you the vibration mode, depending on small round of errors, it can come up with any combination of alpha and beta. Furthermore, the chances are that that will happen even if the frequencies are not exactly the same but very close. So what can happen is that as you change the design and the two frequencies move together, all of a sudden Abacus or Nastran will change on you the shape of the vibration mode. That is, you may have, for example, a vibration mode for a beam which is symmetric and a vibration mode which is anti-symmetric, and you analyze them, and always one of them is symmetric and the other one is anti-symmetric. So you have a beam and one mode looks like this and the other mode looks like that. And you start optimizing the beam, and you'll tend to put more material in the middle. And all of a sudden, the two vibration frequencies become the same, and your finite element model gives you a vibration mode that looks like that, because it's some combination of the two modes. And, well, it's not going to be as wiggly, but yeah, you look at it and you say, cannot tell physically what's going on. Now, if you were fortunate and you designed the beam and you saw the progression, you'll know what's happening. Occasionally, you'll analyze a structure that somebody else optimized, and you look at the vibration mode that gives you a problem, and you will not be able to see any physical correspondence, why it is vibrating in this strange way. And if you didn't pay attention to the fact that you have two vibration frequencies that are almost the same, you will not be, all of your physical understanding of the vibration shape will be lost. Furthermore, this creates problem in calculating derivatives. And so I want to show you the results of an example that I'm going to actually do numerically in a moment. I generated this from MATLAB, and it shows mu1 and mu2 as a function of one design variable. The design variable is called x, and the other design variable is y, and I set it to 0. So notice what happens here. I have, for negative values of the design variable, one frequency goes up and the other frequency goes down, and then they meet here, and each one of them changes direction. That is, they make sort of a 90-degree turn, and you can see that calculating derivative here is not going to be very productive. So this is the kind of behavior that you encounter even for eigenvalues when you have repeated vibration frequencies. The eigenvalues are continuous, but they are not differentiable. Now let's see how we calculate this graph. And so here is the mechanism for calculating derivatives. Let's say that we have m repeated eigenvectors, so m repeated vibration modes. From what I showed you, any linear combination of those vibration modes is also a vibration mode with the same frequency, so I wrote it like that. That is, and I have to apologize that occasionally, I mean, the subscript I should be a superscript. That's the way it is in the textbook, and from time to time I forget and make it a subscript. So we write that as a matrix U, and in that matrix U we just put the vibration mode right next to each other as columns, times a vector Q, which is how much of each one of them we take. And we say, this is the general vibration mode that corresponds to the same vibration frequency. Here is the derivative equation that we had to begin with. We derived it last time. And so I'm going to substitute u here and for the u dx and everything, and I'm going to multiply by u transpose. And if you do that, you end up with this eigenvalue problem. That is, you find that when the modes are repeated, calculating the derivative of the vibration frequency with respect to x doesn't give you a unique solution, but instead you can have an assortment of the mu dx that is obtained from the solution of an eigenvalue problem with the matrices A and B. And if you think about calculating the derivative of mu here, the derivative can be positive with the red slope, or it can be negative with the blue slope. And so it's no wonder that instead of getting one answer, you get a selection. And if you have two modes, then you'll be solving a 2x2 eigenvalue problem. If you have three modes, you'll be solving a 3x3 eigenvalue problem, and so on. And so I'm going to do an example, and this example has two objectives. One objective is just to show you the mechanics of using this equation, and this is the lesser objective. The more important objective is to show you in how much of a pickle we are. That is, not only calculating the derivatives is difficult, that is, we have to do more work for it, but they are absolutely worthless. Okay, so this is what my objective here. So we take this example where k is 2 plus y and 2 on the diagonal and x on the off-diagonal terms, and where the mass matrix is 1, is the unit matrix, and W is the same. And it's very easy to see that, if you set the determinant to 0, you can calculate mu1, 2 analytically, and it's given by the solution of a quadratic equation, and this is the two solutions of this quadratic equation. And this is the way that they look if you plot them. So this is mu1 and mu2 if we plot them for y equal to 0. And if you look at this for y equal to 0, then we'll get 2 plus or minus the square root of x squared. So it doesn't matter whether x or negative or positive, we'll get the same answer. And so that is responsible for that cusp. And the two eigenvectors that we get for x equal to 0, if you look at x equal to 0, then the matrix is diagonal. And the two eigenvalues for y different from 0 would be 1, 0, and 0, 1. That is, we have essentially two uncoupled equations. For y equal to 0, things get messy, but for any value of y besides 0, we have a diagonal matrix with two different eigenvalues, and the eigenvectors are very well defined. On the other hand, for y equal to 0, we will get 2x, x2, and again we will get very well defined eigenvectors that would be 1, 1, and 1 minus 1. So what I want to show you here is that as long as x is 0 alone or y is 0 alone, we get eigenvectors that are very well defined. And then when both x equal to 0 and y equal to 0, all of those apply. So if you think about eigenvalue derivatives, the derivative with respect to x when y is equal to 0 is 0. That is, the eigenvector remains the same all the time. Derivative with respect to y when x is equal to 0 is 0. But when we are in that middle, we get into trouble. And obviously, the eigenvectors are discontinuous because we can jump from one to the other, and things are not defined. Now, any problems with seeing this difficulty that we have, that is, as we approach the point x equal to 0 and y equal to 0, if we approach along the x equal to 0, that is the vertical axis, then we have these eigenvectors. If we approach from the horizontal direction, we have this eigenvector. And then in the middle, we have them all. That is, any vector is an eigenvector. And so this is a bit confusing, but now I'm going to show you where it's going to kill us when we want to use those derivatives. And so we are going to go through the motion of calculating the derivative. And I did this with respect to x. So when y is equal to 0, these are the two eigenvectors, and then we calculate the matrix A, the matrix B, and we calculate its eigenvalues, and the eigenvalues happen to be 1 and minus 1, and it tells us that the derivative with respect to x at that point are either plus 1 or minus 1. The derivative with respect to y, on the other hand, are either 1 or 0. Now we want to calculate the derivative in some intermediate direction. That is, we sort of know how to calculate the derivative in the x direction, and depending on which mode we take, they are either 1 or minus 1. The derivative with respect to y direction, depending on which mode we take, are either 1 or 0. And these are well defined. But what happens if we want to go in some intermediate direction? So I selected this intermediate direction to have dy is equal to 2 dx. That is, we are going in a direction like that. And then we can go back to the quadratic equation that we had and say we are starting from x and y equal to 0. So let's replace y by dy and x by dx, plug into this equation. And we get the d mu is dt plus or minus the square root of 2 times dt. So for example, for dt equal to 1, we are going to have 1 plus square root of 2 or 1 minus square root of 2. On the other hand, if we are using an optimization program, it's going to calculate d mu from this equation. This is the standard equation for calculating derivative in a direction, if you know the derivative in the coordinate direction. And remember that d mu dx is either 1 or minus 1, and d mu dy is either 1 or 0. There is no way we are going to get this answer by combining 1 and minus 1 for the first term, or 1 and 0. Remember that your finite element program is going to choose for you which one of the two it's going to give you, and no matter how it chooses, you're going to get no relationship to the true derivative in that direction. So we have this strange situation with respect to the derivative of the frequencies. We can calculate them in any direction. It's just that we cannot use the derivatives in the coordinate direction to calculate the derivative in a third direction. Does anybody know what is the mathematical terms for a function for which you can calculate derivatives in any direction, but where you cannot use this type of equation to calculate the derivative in an arbitrary direction? The guy who put his name on that is a French guy whose name means cake. Does anybody know what's the French word for cake? Well, I mean, Victor, you do. What's the French word for cake? Gâteau. Okay. So there is a gâteau derivative, which is the the kind of derivative that we have here. That is, you can say that the eigenvalues are Gateau differentiable, which means in any direction that you want to go, you can calculate the derivative, but you cannot decide on what direction to go based on the derivative in the x1, x2 direction, which means that you lose the major benefit of derivatives. You can use the derivative to extrapolate what will happen if you go in a direction, but you cannot use them to decide in what direction to go. The normal kind of differentiability where you can use, this is called Fréchet, it's another French mathematician. So now, with respect to vibration modes, then the situation is even more hopeless in that the eigenvectors are not even continuous, so it's calculating their derivatives is even more hopeless. And there is something very interesting. Even though the utility of these derivatives when the eigenvalues are the same is almost nothing, it poses a very interesting mathematical problem in terms of calculation. Here I showed you the simplest case where we have symmetric positive definite matrices. When we have general matrices, things get much more hairy. And for years, I've had to review paper after paper of people suggesting more and more sophisticated way to calculate these derivatives, where I didn't have much choice but saying, okay, you can publish these papers, even though they are, there is some chance that somebody somewhere will find some usage for them, even though, but the big danger is that people, when they see paper after paper calculating derivatives of repeated eigenvalues, people get to believe that there is some value in those derivatives. And this is the harm which is done by this avalanche of papers that were published in the 1980s mostly and early 90s on these derivatives. Okay, so let's look at some of the questions that I put as bonus problems. So what I want you to be able to explain to other people is why the derivatives of vibration frequencies are such a bargain. That is, if you are designing something subject to vibration frequency constraint, take the trouble to calculate them analytically instead of by finite differences because they are cheap. And then this has to do with what we discussed right now. Why can we use the calculation of the eigenvector derivatives even though they are not really differentiable? And finally, something that doesn't have to do with derivatives, but has to do with finite element analysis. And it's very important because these things applies in spades to derivatives. That is, deterioration of the accuracy of the derivative is even more severe than the deterioration of the accuracy of the eigenvalues themselves. So does anybody know the answer to problem 3? Well, it's a bonus problem, so maybe you don't want to give the answer to everybody else, but this is it. Any questions before we conclude? Okay, I have homework for a couple of you that came a bit late, Brett and Shai Y.